Okay. In this presentation, I will walk you through the history of our setup at DTU, and where we have worked with HPC and thin clients for almost 20 years now. So a little bit about myself. As already said in the introduction, I'm associate professor in HPC in the research section at the department called DTU Compute, which is the math and computer science department that were joined a few years back. And I have also a second role at the university as the scientific lead and HPC architect in the DTU Computing Center. And I have some information about DCC in a second. This is just some numbers about where we are and what we are. So DTU is the Technical University of Denmark. We are the only technical university of Denmark, so we can always claim we are #1 in this country. And here are some key figures. This is an official slide from our administration. I call this the marketing slide. So and you can see here that we are not only restricted to Denmark, we also have a place on Greenland where we have some activities, and we are spread out over the whole country in Denmark, and we even own a ship, which is not indicated here. So we have a research vessel, which costs a lot of money, I guess. Okay, DTU Computing Center. What is DCC? We are a central DTU unit, so we are paid by university budget, and we provide free access to compute resources, HPC, and also for some teaching purposes. We also offer hosting services, so we are a hosting provider for research sections or departments. So they can come to us and ask us to run their Linux clusters on behalf of them, so they don't waste PhD students' expensive research time to do that. I know how that is because I did that during my PhD 25 years ago, and I thought we should have a unit that takes care of that, so the PhD students can do real research related stuff and don't waste time running around in the server room all the time. In the HPC team, competence team, we also do consulting services for all DTU users, and we do that up to a certain extent free of charge. So if there are users, students, or researchers coming, we help them to port software or to give them advice how to maybe change an algorithm or do something else with their scientific codes. And if this is getting larger, we also get some, we ask them to pay some money to us, and then we get some funding in that way. Our mission is to make HPC work and to give easy access to the HPC resources and provide the necessary support that is needed. And as I said before, that can be performance analysis, and we also try new architectures. So one of our goals is to look into the future, looking into what's coming into the market in the next years. GPUs, we started GPU computing already back in 2007, and we do also this consulting and porting work. And we also try to guide users in the HPC landscape. We have several installations at the university, not just at Computing Center. There are also some local departments who have bigger installations, and we try to guide users in the direction where they can maybe get better or more computational time than we can offer with our relatively small environment. Okay, that was a little intro about ourselves. So let's have a look at this history, HPC and thin clients at DTU. So before the year 2000, that was approximately the time I joined this effort, we had already computer rooms for students based on HP Unix servers and HP X terminals. So already at that time, we had a lot of thin clients around. And then we had some other installations for special purpose like graphics and some other things based on other brands. And in around 2001, we exchanged these X terminals from HP by Sunray thin clients from Sun Microsystems, and we also got a lot of Sun servers in-house. So that was the first installation I was very active in that had both HPC and thin clients under one hat, which consisted of those smaller Sunray Sunfire servers to run the Sunray clients, and then 3 bigger SMP machines for the compute heavy stuff. A few years later, we extended it even more. We got more Sunrays, and we started to do something that we still do today. We run the desktop, thin client desktop dedicated on the Sunray servers and push the applications to the big iron, only having the display on the desktop servers. And we also did some experiment with remote access. Back in the time, we did that with a little tool called X11 VNC that can take your X server and puts it into a VNC protocol, and then you can access this from everywhere. And we needed to put some secure shell around it and so on. It was a nice proof of concept, but it was not very user-friendly. And around the same time, in 2004, we learned to know about a product called ThinLinc from a Swedish company called Cendio. And we contacted them, and they said, yeah, there's this product, but it won't run on your Solaris Spark machines. And then after some meetings, we convinced the company to make the port it to Solaris on Spark to make a commercial product out of that one. And we were the first customer of that one. So we pushed the development of ThinLinc on Solaris, and we were the first customer for it. Then again, 4 years later, we still had around 400 Sunrays on campus. We switched our Sunray servers to some UltraSpark T boxes, which were very nice for that purpose. The big iron, we got 2 more machines and also some smaller workstations. And we started to add some x86-based clusters to the system. And the workload distribution at that time was done, batch jobs were scheduled by Grid Engine, also from Sun. And the interactive work we distributed via in-house scheduling system. And again, as I said, I mentioned that before, the desktop servers, they serve desktops only. All the big applications are pushed to the backend clusters. Then there was another disruption in our environment, because around 2010, more and more students brought their own laptops, and also the university encouraged them to bring their own laptops. And due to the buyout of Sun Microsystems by Oracle, the Sunrays were no longer affordable for us. There was some change in licensing, and there was no further development. And also we could see that ISVs no longer supported Solaris and Spark for applications like MATLAB and other applications that are crucial for an engineering school like ours. So we got away from the Spark iron and moved to x86 64 based hardware only. And at the same time, we actually started DCC. Before that was done in a collaboration between some IT departments and myself. And in around 2008, we started DCC, and in 2010, we started also this hosting business for other departments. At the same time, we changed our scheduler from Grid Engine to Moab, and we dropped our in-house system for the interactive work and integrated this into Moab and Torque as well. So now everything was running in a scheduler, even the interactive work. And then now, 10 years later, we still doing things in that way. We again changed some things. We now run the ThinLinc servers on some AMD servers. And if you are familiar with those Opteron CPUs, you can see they are quite old, but they are still serving as well. So we have those 4 servers. They serve between 400 and 600 sessions on a daily basis. On the backend side, we have 16 application servers that are based on Intel, Xeon, Haswell, and newer. We added some nodes recently into the environment for GPU visualization via virtual GL. And we also have some GPU nodes in the interactive pool that have state-of-the-art Volta V100 GPUs for people doing developing and interactive work on those machines. And all the scheduling in this interactive environment is now done by PBS Pro, the community edition. On the HPC side, which is fully integrated with the desktop environment, we have 150 nodes of different CPU flavors. We have about 22 nodes for GPU computing, where each node has at least 2. Some of them have 4 GPUs ranging from Pascal and Volta, and we do the scheduling via IBM's LSF. And this public part means that all the DTU users have access to that one. They don't need to ask. They can just use their DTU credentials to log into the system. And besides that, we also have those hosted clusters, which about 300 nodes paid by different research units and departments. And they have restricted access, but they also integrated into the system. So all the nodes run Scientific Linux 7. We have the same software stack, and we do resource pooling. So we allow overflow between queues based on some policies, and also sometimes some manual interaction. So how does it work for the interactive part? So the access to the system is via ThinLinc. So you do a remote desktop session, or for the command line oriented users, we also provide secure shell access. So if people use ThinLinc, it looks like that. So either they come from a stationary machine or their laptop, and then they log in with ThinLinc, they get the desktop, and from that desktop they can launch either interactive work that goes into the green cloud to the right, or they launch batch jobs, which ends up in the blue cloud to the left, and under those clouds are racks with servers. And as you can see here, there is the application side where we have the 16 servers that I just talked about, and on the other side over here we have those clusters from the different research units and departments with the corresponding queue names. So now if a user logs into the system and starts an application from the menu, we have the scheduler in between, and then let's say there's a MATLAB user starting MATLAB interactive, then the GUI will go, MATLAB will be launched on the green side, and the GUI is shown on the ThinLinc desktop. And we do this for different things. Since this system has also been used extensively for teaching, we also see something like Office applications popping up in this animation here. But now that everybody brings a laptop and we have campus licenses for most of those software packages, this type of usage for teaching has been going down over the last 5-6 years. Here's a not complete list, just a quick overview over the applications we provide in that way. So we have the typical engineering things like MATLAB and Maple for education, COMSOL, ANSYS, Fluent, Abacus, some statistics packages, and a lot of development tools that are also available. And the nice thing is that some of those applications, when we install them, we integrate them with a batch system. For example, MATLAB, we have some setup that integrates with the LSF backend, so people can start parallel pools from inside MATLAB in the GUI under ThinLinc, and also Abacus and some of those Fluent tools. There, people can set up their simulation in the GUI and then press a submit button, and then the batch jobs are scheduled in that way. In the interactive side, we have a little code of conduct for our users that you can see here. So we put some limits to avoid that people are overloading those nodes with their interactive work. We put some maximum CPU usage and some maximum memory usage. And then we tell the users if they need more resources, they have to learn how to use the batch system. Okay, a little bit about our experiences. So some of the advantages and the synergies we have seen over time is the one software stack on all machines is really nice, because when people are used to run applications on the desktop, they can often, without any modification or minor modifications, also be submitted as a batch system, as a batch job. The data analysis and the software, they are on the same system, so there's no need to move your data to your analysis tool, which with the amount of data that people produce these days can really be a problem. As I said, we have over the last year integrated our visualization machines into the ThinLinc environment, so we use virtual GL and schedule those sessions via PBS Pro onto machines with GPUs, and in that way that people can run ParaView and other heavy stuff in the ThinLinc environment as the normal desktop application. And we still keep this idea of splitting the desktop servers and the application nodes to make the system more stable, and this has been really valuable. Because in the beginning we had some ThinLinc servers where people could start applications on the server side, and then if they took down or if their application crashed and took the server down, they also hit a number of other users. And in our setup, this has, I think we had one ThinLinc server crash in the last 2 years that I remember. So, but we see sometimes that people can take down those application nodes with misbehaving applications. So this gives us a very robust system. Other things, yeah, since we have everything in one installation, we can get a good overview over our resources, and we also pool the resources. So we make agreements with for our hosting part, that if Department A is not using their machines all the time, we make some policies that jobs from other departments can be scheduled onto their machines, typically short running jobs, less than an hour or 2 hours. So if they need their iron to do computing, they can get it back within at least 1 or 2 hours fully. And another thing is that the students have the access to the system in principle when they start at DTU. And there is no new system to learn when they start their projects, either for their bachelor or Master of Science projects. So that has been very useful. But as you can see here on the challenges side, what we see, at least in the last years, is that our new students, they lack a lot of skills. So this is getting worse and not better over time. So I guess they have some other skills, but basic compute skills and how to use a computer, this is more like drag and drop mentality. So for them, it's a big hurdle to get started to use it. And since we also don't use these systems any longer in the first year teaching, as we did earlier when we had only centralized licenses for MATLAB and Maple, so every student was in principle forced to use the system. Now they are only exposed to the system in some courses, and if we force them to. So this is the challenge that we have today in the environment. Another challenge is that sometimes users manage to break out of our scheduling policy and they find a way to start applications on the desktop servers. And this is something we try to avoid. And also we had some ideas how we could confine them, for example, using C groups, but then systemd on Linux got into the way because this breaks some of those ideas. And I guess also in the ThinLinc community, there are some discussions in that direction that I could find in the ThinLinc user group archives, that people have tried that and then also got hit by the same problem. Another challenge is new technologies. What is very hot topic at the moment is using Jupyter notebooks for everything. I call that Python in the browser. This works nicely if the browser and everything runs inside our ThinLinc environment, but people want to run the browser on their laptop and have the compute backend in our cluster system, and that doesn't work because there are some gateway hosts and some other restrictions that don't allow for that one. Then people want to run containers like Docker and so on, and we see that this is not so much about the interactive part, but we see this as a request, and we have some security concerns here. And what we also see is machine learning and AI are really getting big, so we get increased need for resources, but we also see that even people are asking for 1 or 2 GPUs, the way they use the resources is not very optimal. So we need to do a lot of monitoring here and also teach users to make better usage of the resources. Okay, let me conclude to stay close to the 20 minutes that we promised. So I think there's a need for interactive HPC. And for me, HPC has, from a personal point of view, always been an interactive, there has always been an interactive part, but maybe because I grew up from the command line and trying to combine several workstations into a cluster and so on. But I think there's this need for many people, either in the development phase that can be coding native C++ or Fortran or whatever language you code, even to developing a workflow in a more advanced application like MATLAB or ANSYS, Fluent, and so on. There will always be a phase where people can have a benefit of doing this in the same environment where also the HPC execution takes place via the batch system afterwards. And then the nice thing is you have everything in one place. You avoid different copies on your laptop and the HPC environment. You don't need to move the data. And for me, this increases at least my productivity. In fact, I have a laptop, but I use the laptop just as an intelligent terminal. So I have almost no data or code of my projects on my own laptop. And then what I said, what our experiences are, to summarize that. So the needs and the user skills, they change over time. So the needs increase and the user skills, unfortunately, decrease. That's my impression at the moment. And we have to do something about this. That can be training or some other kind of support for the users. And what also is needed, that the users need to change their mindset. I tell them all the time when I teach students and show them the system, I tell them you need to leave your comfort zone and leave your laptop. There's a world outside your laptop. And then many students get really nervous when I say that. But when they started using it, our experience is also that they are really happy about it, and they can see that there's a big benefit that they can go beyond their laptop and have something like ThinLinc and a batch system to extend the capabilities of their own computers.